Hi, I'm Ranshi Cho, a PhD student from the University of British Columbia. In this video, I'll be talking about deterministic atomic buffering, a low-overhead deterministic GPU architecture for reduction workloads. GPUs are extensively used to accelerate parallel workloads, such as machine learning. In this illustration, we perform the same training process multiple times, using the same training dataset, the same GPU, and the same hyperparameters, and we get several trait networks that should have the same accuracy. However, this is not the case, and we have observed an accuracy range up to almost 3%, and this is because GPUs are not deterministic. This makes hyperparameter tuning very difficult, since we don't know whether the accuracy change is due to the hyperparameter change or from GPU non-determinism. To understand the non-deterministic convolution algorithm, let's look at what's happening. In each batch, we convolve the input with the output gradient, and atomically add the result to the weight gradient. Atomic adds are used here because multiple batches are processed in parallel, and all of them atomically add their convolution result to the weight gradient. The way that convolution splits up the total amount of work into chunks, where each chunk calculates a partial result, and atomically adds it to memory, is how reduction workloads are structured. So how are reduction workloads non-deterministic? To demonstrate this, let's look at a simple strawman reduction example with 3 threads, each atomically adding a floating point value to global memory. Because the order of atomic operations is different, the final value stored in global memory is also different, despite them being mathematically the same. And this is due to floating point rounding. To make this program deterministic, one way is to guarantee that the order of atomic operations remains the same across executions. Our work focuses on providing deterministic execution only for GPU reduction workloads, which are commonly found in neural network convolution and graph workloads. Next, we demonstrate at a high level how we order atomics in DAB. In this example, we have 3 warps from different SMs, each executing instructions independently from each other. They each have their own PC that advances on their own. In DAB, instructions in the warp are allowed to freely advance until it hits an atomic instruction. Once all the warps are stopped at an atomic, we then let the atomics issue in a set order. In our case, warp 0 goes, then warp 1, then warp 2. After that's done, the warps are free to execute again. In this video, we introduce deterministic atomic buffering, which tackles non-determinism by composing limited buffering and smart ordering. We first describe how we limit buffer area, then we talk about ordering. We break out the discussion of ordering into 2 levels, locally within an SM and globally across SMs. Then, we present related work, results, and conclusions. Let's dive a bit deeper into how we enforce integral ordering without completely serializing all the atomics and causing a large performance hit. In DAB, atomic instructions operate on dedicated storage, called atomic buffers, instead of writing to global memory directly. This allows warps in each SM to keep executing atomic instructions freely until the buffer fills up. In this example, atomics in 3 different warps, marked by their color, are issued in an interleaved order, and all these atomics modify the same memory address. When an atomic is executed, it writes the instruction information to the warp's designated atomic buffer, marked by the same color. Atomics keep issuing until the buffers are full, and no more atomics can be issued. This is when we start buffer flushing, where atomics in the buffers are written to global memory in a deterministic predefined order. Once that's finished, we can resume issuing. When the kernel ends, any atomics that remain in the buffers are flushed deterministically to global memory as well. And this is how DAB ensures that the result is deterministic. The key idea is that buffering enables us to decouple the instruction scheduling from the ordering of reductions by using a temporary set of locations to defer the actual reduction, allowing for more freedom. Now, let's see how we should organize or allocate the atomic buffers. Here is an example SM with 8 warps. If each warp is allocated its own buffer, then we need 8 buffers in total. On real hardware, with a maximum of 64 warps per SM, that's an extra 64 buffers, which is a lot of area overhead. To save area, DAB uses a single buffer per scheduler, rather than per warp. Modern GPUs have multiple warp schedulers per SM. In this example, we have 2 schedulers per SM. Warp Scheduler 0 is responsible for scheduling warps 0 to 3, and Warp Scheduler 1 is responsible for warps 4 to 7. Going off this organization, we can just allocate a buffer per scheduler, and all the warps under the scheduler will write to the corresponding buffer. Compared to before, we have effectively reduced the area overhead by 4x. But wait, now that warps share a buffer, the buffer writes may race. So what do we do now? Here, we see the 4 warps from the same scheduler racing to write to the same atomic buffer. To solve this problem, let's back up a bit and introduce determinism-aware schedulers. When warps want to issue atomic instructions, the scheduler will stop them from issuing if it's not their turn. These schedulers have a predetermined order for the atomic instructions and will only let them issue when it's their turn. This guarantees that the order of the buffer writes are always in the same order, and therefore the final result is the same. So let's take a look at how we actually realize the scheduling scheme. The first scheduler we adopted is strict round robin, the simplest but most restrictive scheduling scheme. All the warps are issued in round robin order, and the next warp cannot be issued until the current warp is issued. In this example, we have 2 warps to be scheduled. Initially, warps A and B take turns issuing instructions. Light blocks represent non-atomic instructions with varying latencies. Here, even though warp B's instruction has already finished, we cannot issue a new instruction since we had to wait for warp A to issue first. Next, both warps A and B want to issue an atomic. Since it's warp A's turn, it issues an atomic. Warp B can only issue its atomic when warp A finishes writing to the atomic buffer. Afterwards, the same round-robin order is continued. As you can see, there are many gaps in the scheduling timeline, and this hinders performance. So how do we optimize strict round-robin? Here are some of the insights that we take advantage of. First, the scheduling order does not matter before the atomic operations, and the same applies after the atomic. Thus, we're able to schedule with heuristic-based schedulers, such as greedy then oldest. Additionally, we found that reduction workloads are deterministic as long as the order of atomics is preserved. By eliminating these gaps, we're able to obtain a more optimized determinism-aware scheduler. After executing for a while, the atomic buffer is still up, and we need to write the buffer contents deterministically to global memory and make room for the next round of atomics. However, a major problem is that the interconnect in the GPU is not deterministic. Thus, we propose a buffer flushing mechanism that involves reordering memory packets that arrive in a non-deterministic order and then write it to memory. Please check out the paper for more details on how we order atomics within and across SMs. Combining all the determinism enforcement mechanisms introduced previously, we finally present the complete architecture of DAB. DAB enforces 2 levels of determinism at the intra-core and the intercore level. Intra-core determinism only enforces atomic ordering within a SM, and ensures that atomic instructions write to the atomic buffers in a deterministic manner, which is enabled by the determinism-aware schedulers. To enforce ordering across SMs, we also introduced intercore determinism, where buffer flushes that arrive from a non-deterministic interconnect are reordered at the memory partitions. By first ordering atomics within each core, DAB alleviates the reordering burden at the memory partitions, similar to a divide and conquer strategy. Next up is the related work that we compared quantitatively in the results. GPU-DET is the state-of-the-art deterministic GPU architecture that orders all global memory accesses. In particular, in the presence of frequent atomics, the serialization of atomics causes it to have high overheads, as we will show later in the results. Compared to DAB, even though we do not handle all types of global memory accesses, we greatly relax the restrictions on atomics and allows it to have much lower overheads on reduction workloads. We implemented DAB in GPU sim using NVIDIA's Titan V as the baseline configuration. For benchmarks, we choose ones that stress atomic arithmetic operations. Since DAB only affects atomic operations, benchmarks that don't have atomics should see no change in performance. For convolutions, we tested backwards filter convolutions using CUDNN's non-deterministic algorithm 0. And for graph algorithms, we choose between centrality and PageRank from the Pinotia benchmark suite, which are all non-deterministic reduction workloads. Our DAB configuration uses scheduler-level buffering with 64 entries per buffer, and using our most relaxed scheduler, along with some additional optimizations detailed in the paper. For our results, we compared DAB to GPU sim without DAB as a non-deterministic baseline, and GPU det as a deterministic baseline. On the left side, we show backwards filter convolution performance on each of the 3 layers in ResNet, blocks 2 to 4. So conv21 is a convolution for ResNet block 2, layer 1. And on the right, we have graph algorithms between centrality and PageRank with different graphs. Compared to the non-deterministic baseline, DAB only incurs a 20% performance overhead while providing deterministic execution, and has a 4x speedup over GPU det. Notice that for some benchmarks, we are faster than the non-deterministic baseline. This is because DAB optimizations merge multiple atomics that modify the same address into one, which we call atomic fusion in the paper. This effectively reduces the memory traffic from atomics and obtain a speedup. Next, we evaluated DAB with different buffer sizes. In general, large buffer sizes result in better performance because it reduces the amount of stalls due to a full buffer. However, this is not always the case. For convolutions layers 4.1 and 4.2, having large buffers cause more atomics to be densely bunched together and pushed to the interconnect at the same time, causing an increase in interconnect stalls. Here, we compare strict round robin, the restrictive scheduler, to a more relaxed scheduler using DAB. The more optimized scheduler performs equal or better than strict round robin in all evaluated benchmarks by a geo mean of 15%. In particular, the large improvement seen in convolution layers 2.1, 2.2, and 3.2 can be attributed to having 6 warps active, allowing heuristic-based schedulers more options to select a better warp to schedule, whereas the other layers only have 4 warps active. Now, coming back to the other related works, for software determinism schemes, Kendo introduced weak determinism, which tackles non-determinism on synchronization objects, such as lock acquirers, by tracking a deterministic counter within each thread. This approach, while feasible on CPUs, is unlikely to scale up to GPU thread counts. Kawan et al. Proposed software techniques to address floating point rounding specifically. One method is to order floating point using synchronization objects, which incurs up to 10x performance overhead. Another technique uses a wide superaccumulator to cover the whole range of 32-bit floating point numbers. However, this will require almost a 10x increase in memory overhead to store a full representation, which is why DAB opted for buffering and scheduling techniques instead. To recap, we observed that reduction workloads such as machine learning convolution and graph workloads are not deterministic on GPUs. By taking advantage of a property of reduction workloads where only atomics need to be ordered for a deterministic result, we proposed DAB, a deterministic GPU architecture with low overheads for reduction workloads. DAB buffers the atomics and flushes them later in the execution with a deterministic order. By combining this with determinism-aware scheduling and a reordering mechanism to combat interconnect non-determinism, DAB outperforms GPU det by over 2 to 4x and only incurs a 20% overhead compared to a non-deterministic GPU. This enables us to conduct experiments such as hyperparameter tuning efficiently and have confidence in our results. Thank you for watching the presentation.